quantum entanglement, is there a possibility of communication?
You can teleport things. You can do quantum teleportation to entanglement. Entanglement is if you have two qubits, they can talk to each other in a way like nothing classical can talk to each other. You can't describe one without the other. They have this description where you can't know everything about this entangled state without having both of them together. So they have strange correlations, like I can measure this one without having any access to the other. Yep. My measurement will correlate with what happens to the other qubit. And in fact, my choice of measurement, I can look at different degrees of freedom.
Yep.
I can measure different things of my particle. That does have an effect on what the other person will see. If you share one of these entangled pairs, you can teleport some quantum information through the pair.
And can you measure it?
Yeah, it will move. It'll move from here to here.
So can we transmit a message?
Alice has her qubit, and she measures something.
And they're entangled.
They're entangled,
right.
Yeah, of this bell pair. When she measures it, she knows something about what Bob's going to see. Bob is far from Alice. So Bob measures something and gets something random. But Alice knows something about it from what she's measured. But she has to tell Bob what that is, so they have to send a classical message. And when you do this, you can teleport quantum information.
So let's say, I'm just trying to see what the application of this would be. So let's say, could it be possible in the future, from what we know now, to have an entangled bell pair, I guess.
Mm-hmm.
One is on Earth, and one's on Mars.
Mm-hmm.
And you could send messages.
I could send you a key, just like I told you about before, if you wanted.
All right.
We could do that. We could use these bell pairs to share a message.
So how many years in the research of this field how long have they been researching
How long
this?
have we been working on this?
Because it seems it's new to me, but then again,
Well, people started taking it quite seriously in the 1990s. I suppose the idea is, so Richard Feynman, first of all, realized how difficult it is to simulate quantum mechanical systems. This is the way scientists like to do things sometimes, is they like to use a computer to try and predict what's going to happen.
Yes.
Yeah, it's a simulation, right?
Mm-hmm.
But to describe a quantum system, it just requires so much information, so much space. It's like the description of a quantum mechanical system grows exponentially with its size. You can't do that, but this is now why we want a quantum computer, because we're using classical hardware to simulate something quantum.
Yeah.
Now, if you make your machine out of something quantum, if you build it out of the same thing, I like to think of like forget quantum physics for a sec. Like let's say you want to know everything there is to know about ants. You're an ant scientist. You could write a computer simulation, or you could write an equation and try and predict what they're going to do. But a much better computer you could make would be to go dig a hole in your ground, find some ants, and trap them between two panes of glass, and then just watch what you're doing. Now, how good is this computer at telling you how ants behave? I mean, it's the best one you can think of, right? Because I just made a computer out of ants.
Yeah.
You can't do any better than that.
So the quantum computer is the best at
simulating quantum things. Yeah, right.
All right. Yes.
So by making a computer out of the stuff that you're trying to simulate, or the similar kinds of stuff, or the similar kinds of physics, what Richard Feynman pointed out was it's very hard to simulate chemistry. And if you want to study some medical science or some drugs or some DNA or like the cells in your body, or like how do they interact with your body? These are quantum mechanical effects. So if you want to simulate these things at the very microscopic level, you need a quantum computer to simulate those things. So that's the idea. That was 1982, I think.
Have we made any sort of breakthroughs since we started looking into the technology? I think we're getting somewhere.
Yeah. So I was just talking to somebody at IBM yesterday, actually. They're planning to have 1,000 qubits in 3 years' time, and that's a lot of qubits.
Wow. So what's the current amount? Like 4? At the moment,
well, you can go play with them for free, and they have about 5 qubits you can mess with. But so they Google as well, and IBM, they've now got chips with about 50 qubits on them. My research is on quantum error correction.
Okay, right.
And yeah, as I said, to build a quantum computer big, we need lots of qubits, and they all need to work perfectly,
the same way each time.
Yeah, and they can't go wrong. Like if they get measured by mistake, something like that, your information gets all messed up. And so it's really hard to protect a quantum computer from the start to the end.
Because you can't measure it.
You can't measure it, you can't look at it, and nothing else can either. Like the environment can come in and take a little look, or something else can come see it, or just hit that thing with a photon, and the photon bounces off with some information and it's gone. Right?
Wave collapses. Yes.
It's leaking out, it's going all over the place, or it's entangling to things it's not supposed to entangle to. and that just messes it up. So it's correlating with things it's not meant to. So I work on quantum error correction, which is how do you exactly sorting these problems out. The bits you're going to build, they're going to go wrong, and there's lots and lots of work. People are working really hard in labs right now to get all the noise out of their cube. They're making their vacuum chambers more, sucking more and more air out of them. They're making their fridges colder. They're making the materials cleaner with like less impurities. All these things, but they'll never be perfect. Like that's impossible.
Could it be help? Like, is there anything like with electromagnetic, like or plasma to like get kind of like shield it?
Yeah, they do all kinds of stuff. Like there are people look for the right rooms in buildings just to make sure they're not too near the wrong. Wow. Like if the cables running too close to their lab table, their optical table, that can screw stuff up because of the magnetic field that the current is producing. That's the kind of thing people worry about.
Oh dear.
They build new buildings with the right kinds of foundations, like to make sure they're not vibrating. All kinds of stuff, and they have to tune it up every day. Just the heat, expansion and contraction. They just have to so all the PhD students in the lab, they have to tune these things up they're never going to be perfect, and they're going to go wrong a little bit. So what I work on is quantum error correction, which is how you make a perfect quantum bit, a perfect qubit, or using bad quality ones. And then when you've got your perfect qubit, and then also look at how to make two of those perfect qubits talk to each other. When I say perfect, I mean nearly perfect.
Is one of the ways you do it like parallelism?
Kind of, but it does. Okay. Let's. Or you use a redundancy, right? I mean, we do it classically as well. We do it all the time. If I'm worried that you're not going to get the message the first time, I repeat the message, right?
Right.
This is a kind of encoding, right? If you and then you can check it, right? So if I send you the message 3 times, you can see if all 3 of the messages add up together, right?
Right. Yes.
So and you do it all the time on the. You say,
Are you sure?
you order something. You go to a restaurant and you say, can I get pizza, please? And then the waiter says, "Oh, you said pizza." Yeah, I said pizza. You just repeated the message, right?
Confirmation.
Yes. Yeah, exactly. Right. That's a repetition code.
Yeah.
Right. And we do this classically all the time. Like 4G and 5G, they're made out of. We find all kinds of codes, like error correcting codes, where you work out how to get as many bits of information into noisy bits of information as possible. Because what's going to happen is, when your phone signal is going to lose, bits of information are going to disappear out into the air and they'll never get to there.
Well, I'm with Vodafone and I lose bits every day, every second.
That's it, right? But if you have good codes, then you can still get the message across with the right amount of redundancy. And that's right.
So are you talking about the similar sorts of methods as in classical, like Reed-Solomon coding, adds stop bits, parity bits, that sort of thing?
Yeah, that's right. That's right. No, that's exactly right. But there's a bunch of other so the other thing, so a lot of what I do is I think about the kinds of materials that can exist. So like, how does it's getting a little bit dated now, but we use physics to protect and store information all the time, like in the olden days. Magnetic bits, exactly. Yeah. That's exactly what I was going to say. You have a hard disk.
Yes,
that's a big piece of. And what is that if it's not just physically a big repetition code, right? You have this piece of magnet and it points down or up. Magnetic tape as well in cassettes.
That's right.
And all of the bits agree to point in the same direction. Now they can experience errors, right?
Yep.
You can put, but the point is, so you got all your bits pointing down, and say some error comes in, tries to flip one back the wrong way up, so they're not agreeing. Well, you've got this big magnetic field wrapped, that all the other ones are pulling it back in again. So so the physics is really helping you out.
It's self-correcting.
Yeah, it's self-correcting. That's exactly right. It's self-correcting. Wow. And likewise, transistors. I mean, we use those to do the gates as well, like the operations. Gates, right, they're little switches.
Yes.
And you put a current in there, and that will let the current flow or not flow, and that's your 0 or 1, right?
Yes.
But it's important. I mean, you can't just make that out of anything. It's you have to use a semiconductor with some band gap. So the electrons jump from the conduction band to the so that's kind of the principles of error correction. We do it classically all the time. You do it when you don't even know you're doing it. You're encoding stuff all the time.
Wow.
And but quantumly, we have to do this as well. And that's what we do. So when it's even harder than you think to build a quantum computer. It's not just like how many qubits have you got. You got to get a ton of qubits, and then you have to put those together in a way that you can make one really, really robust encoded qubit. I would call that a logical qubit, made out of physical qubits, like the physical qubits of the ions or the electrons or the spins or the photons or whatever you have in your lab. And and then you put all of those physical qubits that can go a little bit wrong together in such a way that you have one logical quantum bit
that you can use for anything. And so all of my research is about finding the right kinds of codes to use. Like, so you need like different codes are better at different things. Like, and it depends what you're making. Like, some if you have your qubits are on a chip. Because you're using superconductors and they're or silicon chips, maybe they do some of that in new stuff. UNSW. Then they want codes and they have to like be laid out in 2 dimensions. So I do a lot of work thinking about what 2-dimensional codes there are. But some people, like photons, you can bounce them, send them through a fiber optic, or you can send them to space through a satellite or whatever. They don't care if they're 2D. So then you can start thinking about other crazy kinds of codes, different. And we just don't know. We don't know the right way to put all the pieces together yet to make a quantum computer.
Because I guess with all the advances of materials, we're getting closer to advancing this technology.
That's it.
Because back, what did you say, in the late 80s, we didn't have access to a lot of the stuff we have access to now.
Right. No, this technology, and it's been in the last decade or so that companies have really got become quite serious about this. There's a company called D-Wave, or there still is a company called D-Wave, and they made a bit of a splash with producing something, and like scientists had a big debate about what it was really doing. And
is this the quantum supremacy thing?
So Google, that happened last year. That was Google announced its quantum supremacy.
What is that?
I'm not familiar. So we know that a quantum computer can do things that classical computers can't do. But if the quantum computer is small, a classical computer has a pretty good shot at doing a bit better still.
Yes.
Right. And so as I say, it's really difficult to make to build a big quantum computer. We can build little small quantum abacuses, but not big quantum computers yet. And then when do you have enough qubits? So they call this quantum supremacy, when a quantum computer can do something a classical computer can't do.
Yeah. Right.
So they did something that demonstrates that the quantum computer can do something, even though it's might be just trivial. You can do it, and a classical computer can't.
That's right. That's right. It will. So that's what Google announced last year. As they had 53 qubits on their chip.
Yeah.
And they just turned it on to see what it would do, and
that's how I test things too. I turn it on, see what happens.
Turn it on. That's that's right. And what they claim is you can't predict. You can't predict what it would do with a classical computer.
Yeah.
They ask it to do something random. And in principle, like the calculation to predict what that random thing is too hard with a regular. So they predict it. Well, they've, as we build these quantum computers, like classical computers get better as well, because they said, not in 10,000 years could you predict this. And then, but IBM, these guys compete. Yeah. And they say, no, if we took our the biggest supercomputer we have,
10,000 years,
they reckon they could do it in a couple of weeks.
Oh.
Yeah.
Wow.
But with the biggest computer we have, and Google are doing this in a fridge
in a minute
with a little chip in seconds.
Wow.
Seconds.
Yeah.
Wow.
So is there a difference, like, with these quantum computers? Are we at the point where the efficiency to run this system is like 10 times more electricity than a normal computer?
These computers they're not going to replace classical.
they won't work without classical computers around them.
Right.
You can kind of think of maybe a quantum computer as augmenting a classical computer. So maybe maybe computers are going to have a classical and a quantum processor.
Right.
Ooh,
Right.
okay.
Where maybe, you know, there are tons of things classical computers can do. I mean, look at the internet; it's going to be massive one day, right? And but there are some things it can't do. So maybe those things it can't do, we can send that off to the quantum part of the quantum processor, and they'll be working together. And you know, really, the quantum processor, it needs a bunch of classical computers around it just to work as well.
Yep.
Right.
Yeah, no, it's not going to replace.
Yes.
It's going to add. It's going to build on the computing technology we have now.
Could you give us a few examples of what you would send to the quantum computer to get it to speed up?
So right now, I mean, it's hard to know. It's a big problem that we have in research, knowing what we're going to use a quantum computer for. I mean, this is kind of why I think these companies are letting people. Yeah. I think like the dream is really to get school kids learning how quantum mechanics works and trying to teach school kids how to program a quantum computer. Yeah, because you know when you're young and you've got a plastic brain, and it'll you can, because you see all these weird effects. You have it's a weird thing to imagine how you might code these quantum computers, right? Because you don't just have. I don't know if you do any. Well, you know about coding, but yeah, you have what you specify pieces of memory into integers and specify pieces of memory into doubles and floating point variables and this kind of thing. But you'd need even new little degrees of freedom, right? New variables, right? You'd have a quantum variable, and you'd have a qubit variable, right? Wow. And this could be in an entangled state, and you can't look at it either, right? You can't just you put your quantum variable in there, and it's going to be processing, but you can't see it until the very end.
Yes, you have to wait till the end.
So you can't look and see what it's doing.
So you can add it to something, and you can. Oh, can you add it to something? You can
interfere it with something. You're going to need a bunch of new operations.
Right.
You can entangle it to something. Like what do you have in your regular classical computer? You have add and subtract and
like
or and AND gates and NAND gates and this kind of electronics. And we have quantum versions of all of those as well. Yeah, and those kinds of gates do entangling operations. More generally, and you can have phases, and you can interfere with the wave as well. You can change its its amplitude or its phase. And these are all the kinds of things you can control with the quantum bit.
And the way you program that will allow you to do amazing things that a classical computer will just be hopeless at.
Yeah, there are some problems where the classical computer just won't be able to keep up. Right. For example, like you said, chemistry. That was we won't be able to simulate like small molecules or chemicals, chemical reactions, complicated materials. One thing maybe we can learn from a quantum computer. So like, for example, we use heaps of energy in the world just producing ammonium or ammonia. I forget if I mean ammonium or ammonia, but you turn one into the other and use that for fertilizer. And that's the Haber process, right? And we use catalysts, and we put tons and tons of heat and energy into solving this problem. But to produce this because we need it. But plants do it, right? They do nitrogen fixation. They do it without all this energy.
If we could cycle.
Yeah, that's right. If we understood that better, if you could simulate that, then we could save tons and tons of the. Yeah, exactly. Yeah, if we understood that a little bit better, you could maybe imagine producing better solar cells. You could save a lot of energy problems, maybe.
Because I do know, I remember hearing that plants do photosynthesis better than we can. We can't even approach their.
What we can't replicate it.
And glucose.
We're not nearly efficient.
And glucose, right? You know how we use glucose? Apparently, that's the bee's knees. It's better than petroleum, is it? Like
maybe I don't have the numbers on that.
Yeah.
So it's like, photosynthesis and glucose. It's like, well, actually, maybe I got it wrong there. But photosynthesis, if we know how to do it like plants do it, we can just run the whole civilization off.
You can create. You need that to create your atmosphere, don't you?
Oh yeah, we won't steal the plants. Like, we'll leave the plants alone.
Oh yeah, but. Yeah, you can replicate other things when you understand how something.
Oh yes. Sorry.
Operates. Yeah.
Well, plants are taking sunlight and they turn it into energy, right? Energy and food.
Yeah.
And we have solar panels that do that too, but they're not as good as what plants do it.
That's right.
So you can imagine making much more efficient solar panels, and you can
and
That's true.
save energy problems this way.
I mean, nature does a lot of things so much better and more elegant than we do. Like, I remember we were watching, was it you? No, it wasn't you. Someone else. We were arguing about drones.
Mm-hmm.
And he said, there's no way, because we were talking about how they were working out, there was a new startup that would cancel out the noise of the air. And I can't, and the guy said, no, I can't do it. It's impossible. You can't do it. It's impossible. And I said, have you ever seen a hummingbird?
Yeah, right. Exactly.
They don't
silent.
make any noise.
Yeah.
You know, a seagull,
Mm-hmm.
you just hear it. That's it.
Yeah.
Yeah, that's right. Nature's pretty good at finding solutions.
Nature's just kicking our butt.
Yeah.
But then, you know, you look at the jet engine, and, you know, once we work out a few things, we could optimize it and just, you know, take it to the next level. And there was the other thing, you know, once we get a foothold in some technology, it's like real quick. Like, I think it was the Wright brothers was in the early 19th century.
Yeah.
58 years later, we had the man on the moon. I mean, it's that quick. I mean, something like that. I mean, yeah. So what I'm trying to say is this quantum field, this field of research around the quantum mechanics, quantum computing. It might be at its infant stage now, but you just look forward a couple of decades, it might just take off.
Think back to the 80s. You go, in 20 years' time,
Flying
a large
cars.
majority of people are going to have electric cars. Yeah, whatever. That'll never happen. And
Yeah.
ta-da!
You all look at the internet, right? Like, what do people say? My parents got the internet in my house, and it's like, oh, cool, I can send emails.
Yeah. Or the pain that the
got.
kids don't know nowadays of old dial-up. They'll never know our pain.
Oh gosh, yeah, I remember that.
That was tough.
But you know what freaked me out? When I first jumped on the internet, this was late in my schooling, I finally got the internet through a modem, and I went on IRC chat, and I'm like, I'm chatting with someone from overseas.
It's mind-blowing.
It blew my mind, because the only thing I've ever had remotely close to that was watching live via satellite.
Yeah.
And I think, oh my gosh, there's a different time zone. Wow, they're asleep. But nowadays, I mean, we've gotten so used to that. Nowadays, like, they're overseas. It's just going to be so laggy. It's the complete opposite now. It's the thing is gone. The wow factor's gone. But you know, I think that quantum is just going to. It has so much potential, really. But the problem is
probably
we don't
the
know.
next game changer. Would you say in technology?
Could be.
We still he's explained it. Dr. Brown's explained to us in great detail a lot of the things, and I still don't understand.
Yeah.
It.
No, nobody does. So, speaking of the Wright brothers, I heard a story. So apparently, when they first started launching these planes,
Yes.
the military generals, they looked at it and said, "Oh, cool. We could we could just fly that over the trenches and spy on the enemies this way." And of course, that's well, you could do that, but I mean, they do far more things, right? Like the things you can imagine that, like I can't imagine, right? You want, it's really cool that people are allowed to go online and mess with these things now, though, because like some smart kid is going to see some, I don't know, some quantum app or something.
Yeah. So it's just quite simple. We go to whatever Google, you said, does it. We could just go and play it.
IBM, the quantum experience. If you Google IBM's quantum experience, you can get an account and you can entangle a qubit.
I think we should have a go at that. Yeah. And if you can get a whole generation to start thinking about what do you want this to do, and they'll come up with crazy stuff, but someone's bound to come up with, can it do that?
You only need one.
Yeah.
and you're like, once the idea is out there.
Yeah, you need just one Einstein.
Yeah.
What was it? What did he do? I wonder if space and time are like just the same side of a coin, different sides of a coin. He was just stamping. It was a clerk, I think he was. He was
Yeah.
a stamping clerk. Maybe that's how he did it. He was like, "Oh, look, they're the same. It's the same. There's the stamp on the envelope. That's space and that's time."
Yeah.
I don't know.
Well,
you must be looking at the clock a lot if you're a stamping clerk.
yeah.
Yeah. True.
I mean, his ideas had to come from somewhere, I suppose.
Yeah.
True.
Yeah, we have websites where we put our papers before they're published.
Yeah.
Yeah.
Yeah. We'll get those details. We'll post it in the details below so they can check out your research.
Sure.
Well,
yeah. Right.
I'm just picking up pieces of my brain. Sorry. But yeah, thank you for coming down and enlightening us with some of the amazing work that you're doing, and you and your colleagues. And I wish I could say I am now an expert in quantum entanglement, quantum error correction, but not really. But that just goes to show how difficult the field it is. So
yeah.
yeah.
No,
Thank
well,
you.
yeah. No. Thanks for having me. This has been fun.